I wrote the unit test. Here's the spew. And by spew, I mean I equipped all of my layers to output lots of information. And so this should make it so that you can debug your assignments, hopefully. I'll talk about how to use this in just a minute. And first, let me just start with, okay, here's this assignment. It's called backpropagation. What the heck are we doing? We're learning, yes. And we're learning how to learn. There's this big data set called the MNIST data set of handwritten digit. There's a big data set. We're going to use a neural net to recognize these digits. In other words, we're implementing OCR, also known as optical character recognition. Our recognizer only has to handle 10 digits, 0 through 9. All the images are 28 by 28 pixel images. It's a very nice data set. You'll never see a data set this clean in real OCR. But it's a good toy problem to build a neural network against and do some optical character recognition. Okay? Each of these images is a 28 by 28 pixel image. I have already digested it for you and put it into ARF format. What's ARF format? It's that file, it's the comma-separated format that I gave you, the matrix class already loads. It's a really easy format to work with. So you won't even see these pictures. You'll just see these vectors of 784 numbers. Why 784? Because 28 times 28 is 784. Your task is to take these 784 numbers that represent that whole image. If you want, you can take those numbers and load them into a image format and visualize them, and it'll make you feel good. But we're not going to do it. We're just going to feed these numbers into a neural net, and it's going to see. And by see, I mean it's going to do a bunch of math on those numbers to compute a new number, and that new number will be the number 0 through 9, and it will either be right or it will be wrong, right? Okay. Your goal in this assignment is to achieve an accuracy of, where is it? 350 or fewer errors out of 10,000, which is pretty good, right? I mean, that's not, humans can do better, but that's getting to the point where you're getting most of the digits right just based on appearance. If your neural net can do that, your neural network is definitely working correctly. It's training all the layers in the neural network, and that means you're on the right path for everything else we're going to do the rest of this semester. So, you get the objective? Okay. Your output will basically look like this. You'll run the program, and it will just print these numbers. Okay? Now, I said that mine ran in 90 seconds or something like that. I didn't count the time to load the data set. It's a big data set, and it takes some amount of time to even load and parse the darn thing. So overall, it's a couple of minutes, and yours won't be that fast because I write good code and you don't. But that's okay. I don't care how long it takes. We'll just produce these numbers. I don't really want to run your code, so it'd be nice if you could just print these numbers, and then I could run your program and it would just print it, and then I could just say, okay, good enough. Surely, at the graduate level, nobody's going to just print numbers they didn't actually achieve, right? That would be clearly in the realm of academic dishonesty. So I feel perfectly comfortable saying, you know, just go ahead and write a program that prints the number 337 or whatever number you get, and we'll call it good. And then I should also see that if I uncomment that line and go, or uncomment the code that actually executes it, I should be able to produce exactly the same number that you printed. That would save me a little grading time. I don't want to have to wait 10 minutes for every single student. Multiply that by 40, that's a lot of grading time. So it's okay to just print the number as long as you first achieve that number. Sound good? Okay, yes?
Didn't you serialize the neural net so you can just run it? Or
oh, that would be even more awesome. If your neural network is pre-trained and then saved into, say, JSON format or some other format, and then you run your program and it loads it from disk into memory, and then runs on the test set, and then produces that number, you've accomplished something really cool, and yeah, thumbs up, please do that. But you don't have to. as long as you train and test a neural network and it achieves a number less than 350 on the test set of 10,000 handwritten digits on MNIST, I will be happy. And to be clear, you cannot use those 10,000 in your training. That's basically giving it the opportunity to memorize those 10,000, and of course it will do well. So you should train on the training portion and test on the testing portion, and you should achieve that number. Any question? Yes?
So what is the exact output? You just want us to print line whatever last value we get?
Yep. I just want to see a number. And it'll be about 300 and something. Yeah, each of these is one epoch. Is it pronounced epoch or epic, or does anyone know, or is it an ambiguous thing?
Do you care about the topology?
Define epoch. What's that? Do I care about the topology? A particular, let's see. How can I get pronunciation? I've always said epic, but it's epoch or epoch. We're both right. Okay, cool. Sorry, what was the question?
Do you care about the topology?
I don't care about the topology. If you use this topology, this is a really lightweight topology and will achieve these results pretty fast. If you want to use a bigger one, I'm okay with that. Yeah. It's probably possible to achieve this level of accuracy if you only have a 2-layer neural network, but it's really, really wide, meaning has 2,000 or more nodes inside of it. But I still think you wouldn't get it working unless you correctly implemented backprop. So I think if you can achieve that level of accuracy, that means your backpropagation is working. So yeah.
Is there a reason you kind of funneled down the weights? I know you eventually need to get to 10, but what if you went from 784 up to 800?
Oh yeah.
Down to 300 and then down to 10?
Is this the correct shape? I have fiddled with it a little bit. I tried probably 10 different topologies, where topology refers to the sizes and numbers of the layers. This one seemed to work pretty well, and my other reason for using that start with a lot and then funnel down to few is, if you remember reading assignment number 2, paper number 1, these guys achieved awesome results. They got down to, was it 19 errors? No, 30 something errors. And why is it sideways? But if you look at their sideways topologies, you'll see they start at 2,500, then 2,000, then 1,500, then 1,000, then 500, then 10. Question we might ask is, did they have a reason for doing that? I'm sure they did. That's all I know. I've tried it with equal size followed by 10. It doesn't seem to train quite as efficiently. It seems to waste more weight. So I think this triangle shape seems to be good. Why? I have no idea. That's about all I got on that. So when it comes to what topology is best, the answer is trial and error until you find which one does the best cross-validation accuracy. And I know that's kind of disappointing, but that really is the best answer. I mean, that's the way to find the answer for sure. There's probably some intuition for why that is in general. I just don't know what it is. I kind of think the field's not even old enough to have really developed that strong of heuristics for driving things yet. So, I don't know. Oh, one other bit of evidence. If you actually study the cerebral cortex of the brain, there is sort of that triangle shape there too that can be found to a certain degree. I'm planning to add some more readings to your assignments. One of them, which I haven't added yet, sorry, I'll get on it, is by this guy who talks a lot about the cerebral cortex, and he argues why that topology makes sense. And things that make sense in the brain sometimes make sense in neural networks too. So there's as much answer as I actually have. Okay. So on assignment 2, we're trying to classify these digits. How are we going to do it? Well, we're going to build a neural network. A neural network consists of layers, and I'm going to draw it like this, but really know that that means it's shaped more like that, right? Where we have some large number of values all feeding in, and all these lines mean they're fully connected, and then those are all fully connected to that layer, and so forth. And I'm going to represent all of that by just drawing a whole bunch of squares with arrows between them. And that means that whatever comes out of this layer feeds into the next layer, and that ultimately produces the output. Okay, so in our neural network, X is 784 values, Y is a vector of 10 values, right? Now in our labels, we actually only have a vector of 1 value. How are we going to get the 10, and what do we do there? Yeah, so if the label is a 3, I'm going to represent that as a 0, 0, 1, 0, 1, nope, 0, 0, 0, 1, because we start at 0. 3, 4, 5, 6, 7, 8, 9. The first thing you'll do when you load your labels data is basically convert them to this one-hot representation. And when I say the first thing you do, that's not actually something you have to do. Just allocate a vector of 10 zeros, and whenever you need it, put a 1 in the right place, right? And then when you're done, put a 0 back there, so now it's clear again, and then next time you can put a 1 in the next place you want. Or if you want to, you can allocate a big 10 by 60,000 matrix and fill them all with zeros and then put 1s in all the correct digits as specified in the labels matrix. If you want to do that, that's fine too. I kind of prefer the generated on the fly method, but it doesn't matter. This is a very, very tiny amount of code, and I think you can all handle that, right? When your neural network makes a prediction, it will not be a binary prediction. It will be a bunch of continuous values, right? Maybe it'll look like 0.1 to 3, 4, 0.2. It'll take me a long time to write out 10 random binary values. Okay. If your neural network made this as its prediction, and pretend there are more numbers after that, is this a good prediction or a bad prediction? Can you even tell? I'm going to say it's a bad prediction because it was supposed to predict a number 3, but the max is clearly right here, unless one of those other future numbers is bigger. And the second biggest is here, and this one is almost 0. And that's the one that should have been a 1, right? And so this is an example of the neural network totally missing the point. It thought that it was a 1, or possibly a 2, but definitely not a 3. And in fact, it was a 3. And so this is the example of the neural network messing up. Okay, yes?
We keep blank here.
Yes.
Should we use the whole representation down there with the doubles and such for computing the blank, or should we convert it to like whatever its categorization is first, and then use the blank?
Ah, excellent question. The answer is use the whole thing. Here's why. Inside of this output layer, there are 10 units, where each unit is one element of the vector that it's producing, right? Okay, well, each of those 10 units is wrong to some degree. In this case, the first unit is wrong by 0 minus 0.1234, so its blame should be negative 0.1234. The second one is wrong by negative 0.43231. The third unit is wrong by 0.331111. The fourth unit, which represents the number 3, is wrong by something like 0.999. It's basically 1 minus that number, right? Because the target was a 1 here, and that's what it predicted. So target minus predicted is a very large number. And what will happen is by putting a big blame on that unit, suppose that's the unit we put a lot of blame on, all of the things connected to that unit will then receive a lot of blame for, because this unit made a big mistake, it's going to pass a lot of blame onto all the units that fed into it, and they're going to pass all the blame back, and that's going to basically shake everybody up, right? And it makes sense that whoever is responsible for a big screw up should have to change their ways. Does it not? And that will result in next time this or similar situation occurs, these weights will be greatly shaken up such that this particular unit will predict something a lot closer to 1, and next time it won't make such a bad mistake. Whereas by contrast, say this unit, which is also connected to everything else, it's not going to change that much because it didn't make that bad of a prediction, right? It predicted 0.1234, it should have predicted 0. Yeah, it was off by 0.1234, but that's only a small change, so it will only change slightly. And thus, in the long run, the whole network is getting closer to making the predictions it should have. Does that make sense? Okay. Did I see a hand? Yes.
So, just to clarify though, the original labels, they won't come out as one hot or whatever. They'll come out as continuous. And then you can
Yes.
hockey and then
When you're measuring the number of errors, so when you're measuring your misclassification rate, now we don't care what numbers the neural network produces. The question we're asking is, was the maximum one the correct one that should have been the maximum one? And if it was, it got it right. And if it wasn't, even if it was off by a tiniest amount, even if it was its second choice and its first choice only won by 0.00001, nevertheless, it's still wrong. So that counts as an error. And so, yeah, we'll measure a very discrete number of errors, but when we're training, we're measuring a very continuous amount of blame.